So, thank you. So let's look at this experiment that some of you may have seen before. Okay?
Would a fly swatter be easier?
Man who catch fly with chopstick accomplish anything.
You ever catch one?
Not yet.
So, like Mr. Miyagi said in Karate Kid, man who catch fly with chopstick accomplish anything. So everybody knows catching a flying fly is hard, even if you have chopsticks. And what we're trying to figure out in our lab is why is it so hard to catch a fly? What are the mechanisms that make flies such good flyers? Here's a movie of a fruit fly we took in our lab using a fast camera working in 20,000 frames per second. So besides watching cool videos like this, let me tell you why I think it's interesting to study why insects fly. So what can we learn for flies? Flight is probably the most difficult form of motion. And in insects, flight is associated with very complicated flows of air that we do not fully understand yet. It's also associated with many subsystems in the animal that have to operate together, like muscles, wings, and control system. In fact, the control system of flying insects is the fastest in the animal kingdom. That is because insects are inherently unstable. They have to constantly control the flight to stabilize themselves, otherwise they would crash, as we'll see. The flight of insects is also important to the ecology. Insects are pollinators, they're pests, and they're a very important link in the food chain. What I like about this field is that it is very interdisciplinary. It lies between physics, biology, and engineering. So our goal is to understand the mechanisms of flight control in insects and then implement them in robotic systems. This is our logo. It's half a fly, half a robot, and today we'll talk about the fly half. So insect flight is a complex behavior. It involves many subsystems. For example, wings, which are extremely complicated. They look as if an engineer designed them. Muscles and transmission system. This is a three-dimensional CT of the muscle and transmission of a fly. You can see it's extremely complicated. These muscles are actually considered the most energy-efficient muscles across all animals. Insects also evolved very specialized sensors, like the organ you see here flapping below the wing. This is actually a mechanical gyroscope, very similar in its function to the gyroscopes we all have in smartphones. These systems are extremely packed inside the animal. For example, this is an image of the smallest flying insect. Its body size is about 1/5 of a millimeter. We can barely see it with the naked eye, but still, it's a fully functional flying animal. All these systems are also associated with very complicated flows of air. For example, like the swirls that we see here behind this fly. Insect flight is also an unstable process. This is because this process is inherently unstable. So here is an example of an insect, a fly, whose control system has been disabled. You can see it can flap its wings, but it falls straight down. It cannot fly. So without a control system, a fly cannot fly. So how do we control an unstable system? We need to have a feedback controller that measures the state of the system and responds accordingly to correct it. So to show this, I have my friend Sam here with me. So Sam has a long stick in his hand, and he wants to balance it. So if Sam doesn't do anything, the stick would obviously fall down because it is an unstable system. But Sam, luckily, has a control system. He can measure the position of the stick and move his hand according to balance it, and is very happy. But what happens when Sam wants to balance a small pen? He just can't do it. Why is that? So Sam's response time remains the same. But the instability time, the time it takes the stick to fall down, is now much shorter. So that is why Sam cannot handle this instability. So we say that in order to control an unstable system, what we need is a feedback controller that is fast enough or faster than the instability that we want to control. But before we talk about the control system of a fly, let's ask, where is it? Where is it in the fly? So here's a fly, and it takes off quite normally, unlike the fly that we saw before that falls straight down. But interestingly, this fly is very special because it doesn't have a head. Yeah, flies can fly without a head, and it means that their control system is obviously not in the head. It's actually located in the central part of their body, next to the wings and sensors. It also means that the head is overrated. So, how do we study flight control in insects? We take fruit flies. These are flies of 3 millimeter length. We film them with 3 fast cameras. We have 2 side views and 1 top view of the same fly flying in a box. And we can also measure the motion of the body in wings, which is represented by this toy fly here. So this represents what we measure about this fly, and this is how it looks. So the fly is flying, and we can see the motion of the body in wings as represented by this cartoon. But this is not enough. What we need is a way to challenge the fly, to change its course in midair, and then to measure how it responds to these perturbations. So how do we challenge a fly? We take the fly, and on its back, we glued a tiny magnet, okay? 3 millimeter fly. And then we can use a pulse of magnetic field to rotate the magnet together with the fly and see how the fly responds to this perturbation. And this is how it looks. So this fly is coming in. It's going to be hit by a magnetic pulse, 1 wing beat long, now. It's rolled to its right and recovers. That's it. So let's watch it again. This fly is coming in. Pulse is 1 millibeat long, 5 milliseconds. This is going to roll the fly 70 degrees to its right, and then the fly fully recovers its orientation after 7 wing beats. That's about 30 milliseconds. So this is very fast. By the time I blink once, this fly could have performed this maneuver 10 times. Okay, so how did the fly do it? So here you see a series of images, 1 image per wing beat of the same fly, seen from the top. So before the maneuver, the fly was flapping symmetrically. The angle of the right wing is the same as the angle of the left wing. But during the maneuver, it was flapping asymmetrically. The angle of the right wing increased, while the angle of the left wing decreased. This asymmetry in angle created a force asymmetry, which is the force that rolled the fly back to course. This is the mechanism. What we also measure is the response time of this reflex. So it's a 5 milliseconds, 1 wing beat response time, which is actually among the fastest response times in the animal kingdom. So the common fruit flies I see in my kitchen coming to rotten bananas are actually the animals with the fastest response time in nature. We also managed to come up with a quantitative description of this control reflex in the language of control theory. So let me show you now an experiment that demonstrates how important it is for these flies to have this fast control system in the wild. Okay? This is the experiment. So we have a guy with a gun and a donut. And this guy is going to kill the donut. Okay, pay attention. Done. Okay, but this was no ordinary guy because he also had a fast camera. And there was accidentally a fly here that was rolled the same way we roll the fly in our controlled experiments. And when we look at this, we see that the response of this fly and the timing of this response are very similar to what we measure in the lab. Boom. Okay, so seriously, flies don't meet a lot of donut killers in the wild, but this response is still very important because flight is very unstable. The instability associated with the mechanics of flight is so fast that flies have to have a response time of about 1 wing beat to stay aloft. Let me tell you for a bit what we're currently doing in the lab. So currently we're trying to challenge these flies even further. So take a look at this one. This fly is coming in, and instead of 1 magnetic pulse, we issue a series of pulses that rolls it over 8 full times. So during this treatment, this fly cannot resist the magnet, but as soon as it ends, it regains control within 1, 2, 3 wing beats, and that's it. So the first thing we learn from these kind of experiments is that it's very hard to make a fly dizzy. So no matter what we did, we never managed to take them off the air. But seriously, what we see is that the control system of these animals is much more sophisticated than we currently understand. We're also looking now on mosquito flight. Mosquitoes are very important insects. They have a lot of influence on humans. They also fly differently. But I could talk about it for hours, but time flies when you're having fun. So thank you.